We are starting 6.3, sampling distributions and estimators. So let's look at what a sampling distribution is. So it's the distribution of all the values of the statistic when all the possible samples of the same size n are taken from the population. So we are going to look at all possible samples. And we are going to use n is our sample size. And we are going to look at how the sample is distributed. So we can look at the sample mean or the sample proportion. We can also look at the distribution as a table, a histogram, or a formula. So the distribution of all possible means is the sampling distribution of the sample mean. So the distribution of all possible means. So you would find the mean of it within each sample. So of course, this is also represented in a table, histogram, or formula. So we are going to look at our first example. A friend has 3 children, ages 1, 2, and 5. Ooh, man. That's a lot of activity right there. 1, 2, 5. Woo. Note that the mean of this population is 8/3. So let's find what that mean is. 8/3, which if we round it to an age, 2.6 repeating. So that's what they're saying the mean of the ages is. So we added them all up, divided by how many kids are, it's 2.6. If 2 ages are randomly selected with replacement from the population, 1, 2, and 5, identify the sampling distribution of the sample mean by creating a table representing the probability distribution of the sample mean. So we are going to find all the samples. So they're selecting 2 ages from 1 to 5, and it says with replacement. So that means we're going to take one of the ages, write it down, then put it back. So we need to know all the possible samples. So we could sample and get a 1 and a 2. We could sample and get a 1 and a 5. We could also do a 2, 1. Even though that's also same as 1, 2, it's still what did we get first? And then 5, 1, 2, 5, 5, 2. Since it's with replacement, you could get 1, 1, 2, 2, and 5, 5. So these are all of the samples of picking 2. So let's find the mean of these samples. What would be the mean if you picked a 1 and a 2? So the mean of that is just, you would add them together, divide by 2. So that'd be 1.5. What about the next one? If we have a 1 and a 5, what's the mean? Okay. A 2 and a 1. A 5, 1. A 2, 5. 5, 2. 1, 1. 2, 2. And 5. And what I should have put up here this is our population mean, but we don't have a population. We have a sample, right? So I'm going to X that out, and it should actually be X bar. So X bar. Because it's a sample mean. It's not the population mean. Or maybe it is the population. Because it's just 1, 2, and 5. It is a mean. We're just going to put on here mean. All right, let's look at the probability. So how many possible samples? What is our sample size? 9. So n equals 9. So each one of these would be 1/9. So we have identified the sample, the mean, and the probability. So let's find the mean of the sampling distribution. Because the above table is a probability distribution, we can use the following formula. Population mean equals X times P of X. So this is our X, and this should have X bar times P of X. So that means we are going to multiply each one of these and then find the sum. So let's make another part to the table. And let's do X times P of X. And then we are going to add them all up. So if we multiply, we would just do top times top, bottom times bottom, or just the 1.5 times 1 over 9. 1.5 over 9. The next one would be 3 over 9. 1.5 over 9. 3 over 9 again. 3.5 over 9. 3.5 over 9. 1 over 9. 2 over 9. 5 over 9. Then we would need to add those all up. So in reality, I could just add the numerators and then put it over the 9. So the sum would equal something over 9. Let's add those up. I would do the 1.5, so that'd be 3. That's 3 more. 1, 2, 5. Go ahead and add them all up. How much is it?
24.
Yep.
Which is 2.6 repeating.
Right. Which is a 2.6 repeating. Right. So we did a whole lot of work for the same answer. So C asks us, the population mean is 8 over 3. Do the sample means target the value of the population mean? So target means be the same. Do they also equal the same? And it's yes, they're the exact same. So it was 8 over 3, which was, we also got 24 over 9, which was that 2.6 repeating. And there's a reason for this, because it says behavior of sample means. The sample mean means target the value of the population mean. The distribution of sample means tends to be a normal distribution, tends to become closer and closer to a normal distribution as the sample size increases. So look at the following example about rolling a die 5 times. Nope, we're going to skip that. And we're going to go to the next one. Sample distribution of the sample variance. So now we're talking about the variance. So we're looking at the sample variances. Typically represented in a table, histogram, and formula. Be sure to use the correct computations for standard deviation or variances, depending on whether you have a population or a sample. So the mean of the sample variance, S, equals the population variance. So this is R2. This is our population variance. This is our sample variance. Okay, so no, that's standard deviation, so it's squared. Forgot the little squareds on there. So we have these formulas: population, standard deviation, sample. Population variance, sample. The behavior of them is that they target. So whatever you get in your population variance should target the sample variance. The distribution of a sample variance tends to be distributed skewed to the right. So if you look at the example, see how this is skewed to the right? So it looks like the right foot. The other one was a standard normal distribution. So this is dealing with your sample means. They tend to be more of a standard normal distribution. But with your variances, sample variances, they tend to be skewed right. Sampling distribution of the sample proportion. Page 256 gives us an example of this. Let me open up my book. That's where it starts. Let's put that 256. Okay, so the distribution of the sample proportions. So here is the notation. We have P as our population proportion, and our P hat, the little hat that's missing on there, is our sample proportion. And the same thing with population proportion and sample proportion. They tend to target. The sample proportion targets the population proportion. And then the distribution tends to be normal. Let's look at example 4. When 2 births are randomly selected, the sample size is what? What's our sample size of 2 births? What are the options? Boy, 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 girl, girl, boy, girl, girl, right? So what is the sample space? What does n equal? N equals 4. The 4 equally likely outcomes suggest that the probability of no girls is 1 out of 4, which is 0.25. The following display shows probability distribution. Ooh, we cannot see that. For the number of girls, then a table and graph describing the sample distribution for the proportion of girls. So we are going to do this. We're going to make it. So number of girls in 2 births. We're going to find the probability, so P of X. So if we have a boy, that's the number of girls in 2 births. So we could have 0 girls in 2 births, right? We could have 1 girl in 2 births, and we could have 2 girls in 2 births. What's the probability of having 0 girls in 2 births? The only option is the boy. So that's 0.25. How many times out of these 4 was the probability of getting 1 girl? Girl, boy, girl. So that's 2 out of the 4. So that'd be 0.5 or 0.50. And then the 2 girls, there's only one option that'll give us that girl. So 1 out of 4, 0.25. So we can make the probability distribution as a graph. I'm going to count this as 0, 1, 2. The highest that we have is 0.5. So I'm going to do 0.25 here and 0.5 here. So this is number of girls, the x-axis, and then the P of X. So X is representing our number of girls. So for 0, we would have 0.25. For 1, it'd be 0.5. And for 2, it would have 0.25. So what does this distribution look like? Yeah, it looks normal. Let's look at the next one example. A quarterback threw 1 interception in his first game, 2 interceptions in his second, and 5 interceptions in his third game, and then he retired. Consider the population consisting of the values 1, 2, and 5. Notice that the proportion of odd numbers in the population is 2/3. So we are going to look at this and look at the proportion of odd numbers. So list all the different possible samples of sample size being n equals 2, selected with replacement. For each sample, find the proportion of numbers that are odd. Use a table to represent the sampling distribution for the proportion. So this is similar to that last one when you had the ages, the 1, 2, and 5. So we can list those out again. And it's with replacement. So 1, 2, 1, 5, 2, 1, 2, 5, 5, 1, 5, 2, and then 1, 1, 2, 2, 5, 5. Proportion of odd numbers. So what is the proportion? If you have a 1 and a 2, how many are odd? 1. So what would be that proportion? Let's write it as a decimal. It'd be half, right? So we're going to do 0.5. What about the next one? Both of them are. So what's the proportion? 1. Next one. 0.5, because only one of them is. The next one, 2.5. Only one of them is. 5.1, both of them are. 5.2, one of them is. 1.1, both of them are. 2.2, none of them are. 5.5, both of them are, right? What is our sample size of the whole thing? How many did we have? 9. So what would our probability be for each one of these? 1/9. Okay, there's actually a better way of writing this. Huh? Yeah. So our proportion for the odd numbers would be, we could either have 0.5 or 1, right? Those are our options. So how many zeros did we have? So that would be 1/9. How many 0.5s did we have? So that'd be 4/9. How many 1s did we have? Yep. That seems like a better way of writing it. You still got to list them out and figure out what they all are. But then you can put it like that, and you know that these are all going to add up to equal 9/9. So because it's a probability distribution, we can use the following formula. So that means we need to multiply these and then add them up. So if I multiply them, the probability times the proportion of odd numbers, what would I get? I'd get 0 here. I'd get, what is 0.5 times 4/9? 2/9, right? And then 4/9. Add those together. 2/3. And isn't that what they told us? That's what they told us it was going to be. So again, this is just reiterating that the sample mean will target the population mean. So, and it is yes. Because it asks, do sample proportions target the value of the population proportion? And that's a yes. Do the sample proportions have the mean that is equal to the population proportion? That's yes. Okay. Estimator. An estimator is a statistic used to estimate the value of a population parameter. You always want to use unbiased estimators. So a statistic that targets, you want it to target. So which ones were the ones that targeted from the population to the sample? That meant that they're the same. So look back through our notes. Which ones were the same? Which ones targeted? So we have right here, sample means target, right? Does a variance target? Sample variances target population variances. And then what was the last one? Sample proportions target the population proportion. So all 3 of those. So the mean, the variance, and the proportion. Whether you look at the mean variance, or proportion, whether it's a sample or population, they will target each other. So we do X bar for the sample mean, S squared for the sample variance, and P hat for the sample proportion. Biased estimators, a statistic that does not target the value of the corresponding population parameter. Those would be the median, the range, and the standard deviation. The only one that I'm wondering about is the standard deviation, because to find standard deviation, it's a squared. Standard deviation is the square root of the variance. So it does tell us that the standard deviation, standard deviation is often used to estimate our population. There we go. This is sample. I always get those confused. And this is your population standard deviation, because the bias is really small in large samples. So if it's a large sample, you can use this as an unbiased estimator. Sample range and median should never be used to estimate the population range or median. Okay, let's list all the different possible sample sizes of size n selected from the previous set with replacement. We're going to look at the range this time. So if we have the sample of 1, 1, what is the range of that? Range means you find the difference between the highest and lowest. So that'd be 0. The next one, 1, 4, 1, 0, 3, 4, 3, and 0. And what's the probability of each one of these? 1/9. I'm going to do it like that. Just so I don't have to write 1/9 all the time. All right, so then we would find the range of that. Let's add these up and then multiply times 1/9. $16. So it'd be 16 times 1/9, which is just 16/9. So that's 1.7 repeating. So it's saying the mean of the ranges is 1.7. What is the population range? How would you find the range of our population? Just subtract the largest and the smallest, right? So we would do 5 minus 1. What's the range of that? 4. Are those the same? No. Nope. So we will not use range as an estimator. And it's because range is a biased estimator. Hey, just a couple of things about why to sample with replacement. When selecting a relatively small sample from a large population, it makes no significant difference whether we sample with or without replacement. Sampling with replacement results in independent events, so that's why that's important, that are unaffected by previous outcomes. And independent events are easier to analyze, and they result in simpler formulas. That is it for 6.3. So you'll have an assignment in Pearson.